Greetings all. This is Fakadu from Youth and Education Support Service. Thanks to Professor Carl Garby from the University of Nebraska-Lincoln Psychology Department. He have given us access to his lecture notes and his exercises for the research design and statistics class. So we have some questions, study questions that he gave us. And I'm happy to share this because he gave us also the permission to do it, to share it widely across the world with whoever is interested to learn more about statistics, about research design, about evidences, and about making informed decisions. So we have here questions about variables, about designs, and about like ANOVA and pairwise comparisons, analytic comparison and trend analysis, K-group chi-square, correlation and comparisons. I have about 13 questions. So we'll go through the questions one by one and the explanation he's giving. I found these questions very interesting because I come from a background without strong statistics skills. So I think it's very important, even if we do this kind of research or not. Anyways, at some point in our career, we at least read research papers or we see evidences, at least we see promotions on television and the like. People try to bring up evidences and figures and then try to say this is that because here we have a figure, here we have the evidence. But as you know, there are a lot of false positive, false negative, a lot of misinformation, a lot of, kind of either people do it intentionally or without intention. So I'm hoping that this message will reach to bigger audience with Ethiopians and non-Ethiopians. As you know, I'm far from home. I'm in the United States and I have students in Ethiopia. So I wish my students, also my colleagues, and especially the PhD and master students might use this knowledge. So we'll start going through the 13 questions and with the answers. And enjoy watching, and please feel free to ask and share it among those in your network. And once again, I would like to thank Professor Carl, a really very, very nice human being, a very great person with a lot of experience. So I love having the chance to be one of your students, and I wish you happy and long life. Yeah, here we go. I have questions. Yeah.
Question 1. Describe the dimensions or attributes used to organize the variety of single-factor designs and explain under what conditions results from which of the resulting designs can be causally interpreted. There are two dimensions. One is the statistical model that's used. And question 1. Describe the dimensions or attributes used to organize the variety of single-factor designs and explain under what conditions results from which of the resulting designs can be causally interpreted. There are two dimensions. One is the statistical model that's used, and the other is the interpretive model, which pretty much has to do with assignment. The statistical model comes in three kinds: between groups, within groups, and matched groups designs. Assignment comes in three parts: a true experiment, which has random assignment of individuals; a quasi-experiment that does not; and a natural groups design, which has neither proper assignment nor manipulation by the researcher. The quasi-experiment is sort of in the middle in that it does have manipulation by the researcher, but it does not have random assignment. A true between groups design can be causally interpreted if there's good ongoing equivalence. The random assignment involved in a between groups true experiment takes care of initial equivalence of subject variables, but we can only causally interpret that true experiment if we maintain ongoing equivalence. A within groups true experiment, which has random assignment, which is now called counterbalancing, also gives us initial equivalence, and we can causally interpret the results from a within groups true experiment if and only if we maintain ongoing equivalence. A true experiment with a matched groups design, after matching, the members of that matched group are randomly assigned to conditions, and so we have random assignment operating in a true matched groups experiment, and that, along with the matching, guarantees us initial equivalence of all subject variables. And so a true matched groups design, like a true between groups design and a true within groups design, has random assignment, gives us initial equivalence, and can be causally interpreted if we maintain ongoing equivalence. The other opportunity for causal interpretation is a within groups quasi-experiment. Now, there is no counterbalancing or random assignment. However, the nature of the independent variable is that that independent variable is seriated. The conditions have to occur in a particular order. In other words, there isn't an order effect separate from the IV. The independent variable is an order effect, that as you get older, scores change. As you practice, scores change. As you accumulate the amount of medication you're given, your scores change. But just like the other situations or the other conditions that, the other combinations that are causally interpretable, we can only causally interpret the results from within groups quasi-experiment if we maintain ongoing equivalence. So the only real change in this from the earlier characterization in quiz 1 is keeping in mind that a within groups quasi-experiment does not have an order effect, is the same people over and over and over again, and so it's the same people that came in the door, so those things haven't changed. But keep in mind that all of the smiley faces require the maintenance of ongoing equivalence, and that's going to be our biggest single problem running research outside of the laboratory.
I'm going to repeat this because I really want to get wholly detailed.
Question 1. Describe the dimensions or attributes used to organize the variety of single-factor designs and explain under what conditions results from which of the resulting designs can be causally interpreted. There are two dimensions. One is the statistical model that's used, and the other is the interpretive model, which pretty much has to do with assignment. The statistical model comes in three kinds: between groups, within groups, and matched groups designs. Assignment comes in three parts: a true experiment, which has random assignment of individuals, a quasi-experiment that does not, and a natural groups design, which has neither proper assignment nor manipulation by the researcher. The quasi-experiment is sort of in the middle in that it does have manipulation by the researcher, but it does not have random assignment. A true between groups design can be causally interpreted if there's good ongoing equivalence. The random assignment involved in a between groups true experiment takes care of initial equivalence of subject variables, but we can only causally interpret that true experiment if we maintain ongoing equivalence. A within groups true experiment, which has random assignment, which is now called counterbalancing, also gives us initial equivalence, And we can causally interpret the results from a within groups true experiment if and only if we maintain ongoing equivalence. A true experiment with a matched groups design, after matching, the members of that matched group are randomly assigned to conditions, and so we have random assignment operating in a true matched groups experiment, and that, along with the matching, guarantees us initial equivalence of all subject variables. And so a true matched groups design, like a true between groups design and a true within groups design, has random assignment, gives us initial equivalence, and can be causally interpreted if we maintain ongoing equivalence. The other opportunity for causal interpretation is a within groups quasi-experiment. Now, there is no counterbalancing or random assignment. However, the nature of the independent variable is that that independent variable is seriated. The conditions have to occur in a particular order. In other words, there isn't an order effect separate from the IV. The independent variable is an order effect, that as you get older, scores change. As you practice, scores change. As you accumulate the amount of medication you're given, your scores change. But just like the other situations or the other conditions that, the other combinations that are causally interpretable, we can only causally interpret the results from within groups quasi-experiment if we maintain ongoing equivalence. So the only real change in this from the earlier characterization in quiz 1 is keeping in mind that a within groups quasi-experiment does not have an order effect, is the same people over and over and over again, and so it's the same people that came in the door, so those things haven't changed. But keep in mind that all of the smiley faces require the maintenance of ongoing equivalence, and that's going to be our biggest single problem running research outside of the laboratory. Number 2, describe the advantages of multiple condition designs, the different kinds of conditions that may be included, and how a researcher decides which conditions to include in a research project. This is one of those ones where I want you to have a set of things memorized that you carry around with you. That every time you're looking at a design, whether it's yours or somebody else's, you sort of tick off the different kinds of conditions that can be in a study and see if they've covered their bases, if there's anything missing, if you need to add anything. The way that we approached this was looking at the different kinds of conditions, sorting those into different kinds of treatment conditions and different kinds of control conditions. The different kinds of treatment conditions are 3. Treatments that differ quantitatively, that differ by amount. How much, how often, how many. The second is treatment conditions that differ qualitatively. What kind? What variety? How? And the third is treatment conditions that differ by combinations of treatment elements. So you got differ by amount, differ by kind, and differ by combination of elements. When we look at kinds of control conditions, we have the standard no treatment control, the classic control condition. We then have what I refer to as a standard treatment control. For most phenomena that we're studying, particularly if it's therapeutic research or any sort of applied research, there is something that's commonly being done now. And that's a reasonable comparison group. There is also a best practice control group, because very often the best thing isn't the standard thing. And if you want to show that your new something rocks, you want to not only show that it's better than nothing, and show that it's better than what's usually used, but show that it's better than anything else out there. The fourth kind of control condition is a pseudo-treatment condition, or sometimes called an all but one control condition. This is when you're trying to identify a particular causal element in a multiple element treatment, and so you run a treatment condition that's everything but that element. The example we used was brain lesions, where you've got another group of animals that get the entire medical preparation, the entire surgical preparation, and the entire surgery, except for the lesion per se. The whole idea is for the selection of conditions, treatment conditions and control conditions, to provide direct tests of the research hypothesis. You have to articulate what you mean when you say this works better. Better than what? The then what's define the conditions you need for your research study. Number 2, describe the advantages of multiple condition designs, the different kinds of conditions that may be included, and how a researcher decides which conditions to include in a research project. This is one of those ones where I want you to have a set of things memorized that you carry around with you. That every time you're looking at a design, whether it's yours or somebody else's, you sort of tick off the different kinds of conditions that can be in a study and see if they've covered their bases, if there's anything missing, if you need to add anything. The way that we approached this was looking at the different kinds of conditions, sorting those into different kinds of treatment conditions and different kinds of control conditions. The different kinds of treatment conditions are 3. Treatments that differ quantitatively, that differ by amount. How much, how often, how many. The second is treatment conditions that differ qualitatively. What kind? What variety? How? And the third is treatment conditions that differ by combinations of treatment elements. So you got differ by amount, differ by kind, and differ by combination of elements. When we look at kinds of control conditions, we have the standard no treatment control, the classic control condition. We then have what I refer to as a standard treatment control. For most phenomena that we're studying, particularly if it's therapeutic research or any sort of applied research, there is something that's commonly being done now. And that's a reasonable comparison group. There is also a best practice control group, because very often the best thing isn't the standard thing. And if you want to show that your new something rocks, you want to not only show that it's better than nothing, and show that it's better than what's usually used, but show that it's better than anything else out there. The fourth kind of control condition is a pseudo-treatment condition, or sometimes called an all but one control condition. This is when you're trying to identify a particular causal element in a multiple element treatment, and so you run a treatment condition that's everything but that element. The example we used was brain lesions, where you've got another group of animals that get the entire medical preparation, the entire surgical preparation, and the entire surgery, except for the lesion per se. The whole idea is for the selection of conditions, treatment conditions and control conditions, to provide direct tests of the research hypothesis. You have to articulate what you mean when you say this works better. Better than what? The then what's define the conditions you need for your research study. Three is really important to me because if you're going to be good at identifying controls and confounds and evaluating research, whether it's your own, your students, your colleagues, or if you're reviewing articles or grants, you have to have some system in your head for how to look for controls and confounds. One of the principles on which this course is based is that I have to teach you the things to look for and get you to actively look for them, because both perceptual and cognitive psychology tell us that we are much better at looking for things than looking at them. And so we have to have a list of things to look for. So the types of variables are the same 8 that we used in exam 1. There's IVs, there's DVs. There's 3 kinds of subject variables. Subject variable constants, where everybody has the same value. Subject variable controls, where different people have different values, but they're the same on average between conditions. And subject variable confounds, where different people have different values, and those values are different on average across conditions. And that's the level of explanation that I want in the essay question. Don't just use the words. Tell me the difference between a subject constant, a subject control, and a subject confound. There are 3 kinds of procedural variables. There are procedural variable constants, where everybody is given the same value as part of the procedure. There are procedural variable controls, where different people have different values, but those values are the same on average between the conditions. And there are procedural variable confounds, where different people have different values on those procedural variables, and there are mean differences across the conditions. How one decides the role of a variable in a particular study. We gave you one script. There's 2 scripts laying out there. One script is given on the variable explication handout. You start with whether it's measured or manipulated. You decide if it's the IV or the DV. If no, you go on. You decide if it's reasonably a constant. You decide if it's a matching or yoking variable. You decide if the design used counterbalancing or random assignment. If the answer to all of them is no, then it's a confound. So that's one good script that we tore from the hearts and minds of a lot of experts. The other slightly different script is given in the demo for quiz 3. Which again starts with determine if it's subject variable or procedural variables at the IV or the DV, then focusing on subject variables versus focusing on manipulated variables. This one is used less often than the other one, but the people who use it really like it and use it really quickly. There's 2 kinds of people in the world, those that divide people up into 2 kinds and those who don't. This seems to be one of the 2 kinds of people. Whether people want to think about the design holistically and think about it as a variable, or if they want to think about it procedurally, or if they want to think about it variably. Yeah. Whether they want to focus on the design or want to focus on the variable. Both work just fine, and in some research we ran, we were able to move people back and forth between the 2 quite well. We could move experts back and forth between the 2 with no problem. We could move 450 students back and forth between them in about 3 trials of practice. We could move 350 students back and forth between the 2 in less than a dozen trials of practice. And so it is an adoptable thing. Now, to answer question 3, I don't care if you pick one and could give it back to me because it's in your head. Pick the other because you can give it back to me because it's in your head, or make up your own. All I care is that it's complete and that somehow it will get you to all 8 kinds of variables. Some people are much more holistic. Some people are much more linear. I want to be sure that you have something that works. It certainly doesn't have to be mine. I've tried to figure out what I do, and I think what I do is really dependent on how somebody's telling me the story, which approach I use. If they're telling me about variables, I seem to do it that way. If they're telling me about designs, I tend to do it that way. It's one of the advantages of doing this stuff all day, every day. You get a chance to get pretty good at it. It's very fun. Number 4, differentiate between the ways of controlling subject and procedural variables and tell why equivalent on the average is sufficient to allow causal interpretability. All right, whether you're controlling subject variables or procedural variables, we really only have so many procedures available to us, and they're pretty much the same, even though they change names a little bit. We have 3 basic approaches. Holding constant, because any variable that's held constant can't be a confound. We apply that to both subject and procedural variables. Elimination. Some people treat that as a separate thing. Some people treat it as a kind of constancy, which is particularly easy to do, seeing as how elimination is defined as constancy at value 0. The other principal procedure that we use for generating control is called balancing. On average, this variable is the same for the 2 conditions. 2 procedures we use to produce balancing are random assignment, sometimes called counterbalancing in within groups designs, and matching. So you can call it 2 things or 3 things, I don't care. You can think of it as constancy, which has a version called elimination, and balancing, which has 2 versions, random assignment and matching. That's fine. As long as you get all the pieces out, how many pieces you say it is, I don't care. Why is equivalent on average sufficient to show causal interpretability of research results? Our causal interpretation of research results is based on average differences on the DV between conditions. So if the IV is the only thing that's different between conditions on average, then the average difference on the DV is attributable to the average difference on the IV, on average. The part that makes that simple is the hardest part to start with. We don't think about the IV as being different on average between conditions. But it is. If it's a constant in one condition and a constant in the other condition, and they're 2 different values, then they're different on average. So when average differences in the IV are the only average differences between conditions, then average differences on the DV can be attributed to average differences on the IV. Just another ordered expression of the same idea. What is the null for ANOVA when applied to multiple condition designs? What is the limitation of this procedure? What do we do to accompany this initial test? How do we choose which follow-up procedure to use? The null for ANOVA, whether for a 2-condition or a multiple condition design, is that the conditions represent populations with the same mean. ANOVA doesn't care whether it's 2, 10, 19, 27, doesn't care. All the same is the null. The limitation for this procedure is that it tells us whether or not there's a pattern of mean differences, but if there is a pattern of mean differences, it doesn't tell us what is that pattern. We have a variety of procedures for determining what is that pattern. We've got pairwise comparisons, with and without alpha correction. We've got simple analytic comparisons. We've got complex analytic comparisons, and we've got trend analyses. Any of those gives us a way to look at the pattern of mean differences after the omnibus F or the omnibus ANOVA tells us that there is one. The way that we choose between those follow-up procedures, like the way we choose among everything else, is we pick the one that is the most direct test of the research hypothesis. If you're telling me about pairwise differences, I'm either going to use pairwise comparisons or simple analytics. If you're telling me how conditions group and those group conditions compare to each other, then I'm going to use complex analytic comparisons. If you're telling me about the shape of the IV-DV relationship for a quantitative variable, I'm going to use trend analysis. We always want to use the most direct test of our research hypothesis. Six, what is alpha inflation and how does one calculate the extent of it for a given set of ANOVA follow-up analyses? Describe the 3 ways to assess experiment-wise type 1 error. Which of these do you prefer? Explain your answer carefully. Alpha inflation is the simple idea that the more statistical significance tests you do, the more you are likely to end up rejecting the null, and the greater the accumulated chance that you're going to make at least one type 1 error. Alpha inflation specifically refers to an increasing chance of making type 1 errors when you make multiple comparisons. There have been multiple attempts to push the notion of beta inflation. They've never gotten anywhere. The idea is that you might have too little power for any of your comparisons, or for some but not others. And it's gotten nowhere, which is a real shame, because nearly all of the mistakes that we make statistically are type 2 errors. We really don't make that many type 1 errors. How does one calculate the extent of it for a given set of ANOVA follow-ups? What we have to do is take into account the risk of each comparison and the number of comparisons. We have 3 ways of assessing experiment-wise type 1 error. One is a priori. We decide what risk we're willing to take for each comparison and the number of comparisons we're going to make. Now, all of this happens a priori, before we've done any analyses. So this is the maximum risk we're willing to take. So if we decide we're going to do uncorrected tests, and we're going to do 5 of them, that's 5 times 0.05, or a 0.25, 25% a priori risk. We start out ahead of time saying the worst that could happen to us is 25%. The second approach is post hoc tests. Post hoc assessment. When we use a post hoc approach, we recognize that we can only make a type 1 error when we actually reject a null. And so what we do here is we look at the number of nulls that we rejected times the rejection criterion for each. So if we have decided that we're going to use an LSD, which is based on a P of 0.05, and 2 of those 5 pairwise comparisons were significant, we have 2 risks of 0.05 or a 0.10 accumulated experiment-wise risk. The last approach is an exact post hoc experiment-wise alpha. By exact, we mean instead of looking at the risk we were willing to take when we rejected the null, we look at the risk we actually took based on the p-value from that pairwise comparison. You can only do that when you can actually get a p-value for each pairwise comparison, and some procedures preclude that. LSDs and HSDs just give you a critical value. They don't tell you what the p-value is, it just tells you whether p is less than 0.05. Other procedures do allow you to do that. So we've got a priori. How many am I going to take at what risk each? That's as bad as it could possibly be. Post hoc, how many did I actually reject the null at the risk I was willing to take? And exact, experiment-wise, is the accumulation of the p-values of the rejected nulls.
How's that different from the post
The post hoc says I got 3. I rejected the null 3 times at the 0.05 level. So 3 times 0.05. The other one says on one of them my p-value was 0.04, on another it was 0.01, on another it was 0.001. And so I would say that my total risk is 0.051, the accumulation of actual estimates of type 1 error instead of just what I was willing to risk. How much am I actually risking? And people who don't like that don't like it because you're making more estimations. People who do like it because your number is always smaller. I mean, you never reject the whole set each at 0.04999999. Right? You're always taking less than the 5% risk you were willing to take. And that's the argument for the exact procedure.
This is a dumb question.
No, please.
I was just going to ask why you would ever not do an exact. It would be because you can't always get the p-value?
Sometimes it isn't convenient. For example, if you want to do LSDs, SPSS will give them to you, but a lot of people don't like the way it calculates the error term. But one of the things that you can do is do pairwise F tests, but then use the error term from the full model and recalculate and then plug that in to web pages that I can give you, and it comes back with an exact p-value. Okay, if you're doing real high-end stuff and it really, really matters, sometimes it's worth taking the 15 minutes. Most of the time, these are hairs that are split here that are rarely split in a journal article.
Just to clarify for myself, with uncorrected, is that the only time you don't divide the number of comparisons by 0.05?
Yes.
Okay.
Yeah, and we'll talk about correction here in a little bit. But yes, correction means I'm going to worry about my overall experiment-wise error by reducing the error rate on each comparison. Okay? One way or another. No, that's a great question. Quit fussing. Seven. Be prepared to describe each of the following pairwise comparison methods or to compare and contrast any pair. Fisher's LSD. Pairwise comparisons without benefit of an omnibus test. You literally go in and do t-tests or f-tests on each pair. Hardly anybody ever does this. What we nearly all do as the most sensitive thing that we tend to do is the Fisher's protected test. We're still doing pairwise comparisons. We're still using LSD, but we only do the LSDs when we have a significant omnibus F-test. The idea is that we protect ourselves from unnecessary type 1 errors in the pairwise comparisons by being sure that there's an effect there to look for. There's a whole bunch of research that suggests that this may be the best balance of type 1 and type 2 errors, but only because we tend to run underpowered studies. And so it's more likely to be right on average. However, the way it raises that average is by increasing the number of type 1 errors to offset the number of type 2 errors that are probably caused by insufficient sample size. It's a weird way to get better. It's frighteningly close to the notion that 2 wrongs make a right on average. Did you ever hear the joke about the engineer, the chemist, and the statistician go hunting? The engineer decides he's going to shoot first, takes a shot, and there's a poof of snow about 3 feet to the left of the deer. What did I say, an engineer and a chemist? The chemist takes a shot, a little poof of snow almost about 3 feet to the right. The statistician stands up and says, "We got him!" on average. Reminds you just how shitty and meaningless an average can be. And we'll see more of that when we get to factorial designs. In Tukey's HSD, Tukey said, come on, what we're really going to do is look at all the pairwise comparisons. And come on, we really don't want alpha inflation to go crawling around giving us false hopes. So what we're going to do is we're going to plan ahead of time to correct for the full set of pairwise comparisons so that overall we have an experiment-wise alpha rate of 0.05. Chaffee wanted to do the same thing, only Chaffee thought that we should protect ourselves against all possible comparisons, which at least meant all simple and all complex comparisons. And in some renditions of his work, he didn't write this, but some other people attribute it to him, should also include all of the possible trend analyses if it's a quantitative independent variable. Which, yes, literally means that we're going to have more correction for a quantitative IV than for a qualitative IV with the same number of conditions. Right? Because if you got 5 conditions, you've got 10 pairwise comparisons, you've got 32 complex comparisons, and you've got 4 trend analyses. You're not going to correct for the trend analyses if it's a qualitative IV, but you are if it's a quantitative IV. So we're actually correcting differently based on the nature of the IV. Bonferronis and Duns essentially looks at Chaffee and Tukey and says, not always. Sometimes we only want to or need to use a subset of the available pairwise comparisons, and what we need to control for is just the ones we actually make. Have I told you about my Tukey dream? Okay. So well, sometimes I have this dream that I do a Bonferroni correction, then I sneak a peek at one of the other pairwise comparisons that I didn't correct for, and John walks into the room. Now, I've never met John, but I have seen pictures of him. And so John walks in and actually does this to me in my dream. So of these 5, we have 3 different kinds. Fisher's is neither protected nor corrected. Everything's at 0.05. Here we go. Fisher's protected test is protected, but not corrected. We don't adjust the p-value. We just have increased hope that we're going to find something that's really there because we know there's something there from the omnibus test. Tukey's, Chaffee's, and Bonferroni's are unprotected because they do not require the use of an omnibus test, but they are corrected. The pairwise comparison or the individual comparison p-value is chosen so that they accumulate to an experiment-wise of 0.05. Number 8, distinguish between simple comparisons, complex comparisons, and trend analyses and tell when the results of each can be causally interpreted. Simple comparisons are the same thing as pairwise comparisons, except that we traditionally do no more of them than we have degrees of freedom. So if we have 5 conditions, we do 4 simple analytics instead of all 10. Complex comparisons allow us to compare groups of conditions to each other instead of one condition to each other. Trend analyses only can be used when we have a quantitative independent variable and are used to describe the shape of the IV-DV relationship. And as I said before, pairwise comparisons and simple comparisons are the same thing except the number of them usually done. When the results from each can be causally interpreted, this is almost a red herring question. Whether you do pairwise, simple, complex, or trend analyses has nothing to do with the causal interpretability of the results. The only thing that influences the causal interpretability of the results is whether or not the results are causally interpretable. You have to have a true experiment or a quasi-experiment within groups design that is without confounding. Then you're causally interpretable. Distinguish the information obtained from a trend analysis versus from a series of pairwise comparisons, and give a carefully explained example of each being used when the other should have been. Trend analyses tell you about the shape of the IV-DV relationship. Pairwise comparisons tell you how each condition mean compares to all of the others. When these get confused is most easily highlighted in the situation known as successive differences. When the hypothesis is every time we add IV, the DV changes. A linear trend can happen when you have successive differences, but you can have successive differences that have a shape other than a linear trend, and you can have a linear trend without having successive differences. We drew that out once. Sit around and play with it a bit. But that's the easiest way to put together an example of how one should be used instead of the other. If you're talking about a linear trend, don't do successive differences. Do a trend analysis and see if there's a linear trend. If the hypothesis is about successive differences, don't do a linear trend, do the pairwise comparisons and pull out the successive differences. Does that make sense? Okay, if you're talking about shape, do shape. You're talking about a pattern of differences, look at the pattern of differences. Make up some example from your own research area. What I'd like you to notice is that 16 and 5 are the same question, one for ANOVA and the other for chi-square. What is the null for chi-square when applied to multiple condition design? What is the limitation of this procedure, and what do we do to accompany this initial test? How do we choose which follow-up procedure to use? If we have more than a 2x2 chi-square, the omnibus tells us that there's a pattern of response differences somewhere, but it doesn't tell us where. We have two different approaches to follow-up procedures. One is pairwise chi-squares. We do a whole bunch of 2x2 chi-squares and tear that pattern apart so that we can compare the pattern to the hypothesized pattern and also explicate the existing pattern. The other approach, which is more often applied when your dependent variable has multiple conditions, multiple response options, is to do a goodness of fit across the DV response options separately for each condition of the design. The way you pick between these two is based on the expression of the research hypothesis. If the research hypothesis is expressed as how conditions differ from each other, you're going to need those pairwise comparisons. If the research hypothesis is expressed as the response pattern for each separate IV condition, then the goodness of fit chi-square approach is the more direct test of that research hypothesis. So 5 and 16 both remind us that omnibus tests only tell us if there's something to look for, not what to look for. That we have multiple follow-up options, and we pick the one that is most akin to and the most direct test of the research hypothesis. Please.
I wrote down the part where we use the goodness of fit. I missed the part further.
If the research hypothesis is expressed as condition comparisons. So if I say males are more likely to pick chips over crackers and popcorn, Females are more likely to pick popcorn over crackers or peanuts and chips. That's a goodness of fit test. You tell me if I got each of the things I hypothesized. If I say guys are more likely to pick chips than females, now I need that pairwise comparison. I'm likely even to use a complex comparison where I put chips and I collapse peanuts and popcorn. Because all I really care about is whether the proportion of chip choice is different for boys and girls. Okay? Again, the idea is to tailor the follow-up to the most direct possible test of the research hypothesis. If you start using chi-squares and then move upstream to logit models and some of that other stuff, you get really creative about using things that are like complex comparisons that make more sense in chi-square than they made in ANOVA. Because in chi-square, complex comparisons can be the basis for more precise tests instead of less precise tests. If more of you were likely to do that, we'd spend more time on it. But I want you to see the two different times that are coming. And if you start doing a bunch of chi-squares, come on back because I love that shit. We also teach a module during the summer that's called Alternative Regression Models. That's for when we're working with qualitative outcome variables. We look at log linear models, logit models, and logistic regression models in their various forms. And so if you're going to be working with qualitative outcome variables, there's something in place to take care of you. Okay, it's a little too infrequent to spend more time on here. $17 is just like 6. The difference is we use LSDs and HSDs when we're doing ANOVA to compare means. We use uncorrected tests and Bonferroni corrected tests when we're doing chi-squares. What is alpha inflation and how does one calculate the extent for a given set of chi-square follow-up analyses? Describe the 3 ways to assess experiment-wise type 1 error. Which of these do you prefer? Explain your answer carefully. I should say that on both 6 and 17, I really don't care which one you prefer. I can muster a good argument for all 3 and don't like any of them because it's very difficult to unify the 3. So you really are free to pick whichever one you want. The point is articulating your reasoning. Okay? That's what I care about. There are some things that I feel so strongly about that I've only showed you one version. Like error terms for calculating certain things. Haven't even brought it up. Probably shouldn't have said it now. Okay? There are other things that really are up for grabs in our community. And it would be dishonest to not put them up for you. All right, so alpha inflation is the idea that when you have a multiple condition chi-square, the omnibus chi-square doesn't tell you what you need, and you're going to do follow-ups. And so the more significance tests you do, the greater the chances that you're going to reject some of them, the greater the chances that those rejections will accumulate to at least one type 1 error. The extent for a given set of chi-square follow-up analyses is based on how many analyses you did and the probability of a type 1 error for each. There are 3 ways of calculating those. A priori, you figure out what your rejection criterion is going to be, your p-value, and how many pairwise comparisons you're going to do, and you multiply those 2 together to get the worst case experiment-wise type 1 error scenario. It's based on how many you're going to do and what risk you're willing to take for each, a priori. Post hoc means after you've done your follow-up analyses, you look at how many you actually rejected the null. Because only for those that you reject the null can you really make a type 1 error. You then look at the number of times you rejected the null and multiply that times your accepted rejection criterion. Whether it's 0.05, 0.01, 0.0167, whatever you did, corrected or uncorrected for each. The third is an exact post hoc procedure, which requires that you have an exact p-value for each follow-up analysis, and then you add up the exact p-values from those analyses for which you rejected the null. That can be a little cumbersome for chi-square, actually less so than F, because it's easy enough to get on a web page that calculates exact p-values, stick your pairwise into the computator, stick that chi-square, push a button, boom, you get an exact p-value to like 13 decimal places. Then you add those up for all the ones that are significant by whatever significant standard you set. Number 12, describe how to identify when to use each of the statistical models we've worked with in this unit. And there's the list, but it's in parentheses, so the list won't be there. You got to know the 9 in your head. Okay? And again, you don't have to use my perfectly workable, hard worked on, carefully researched script. You can use anything you want. But I'm going to go through this one. There's 4 different questions that you might have to ask. What kind of variables do we have, qualitative or quantitative? What kind of research hypothesis do we have, association or mean difference? What kind of design we have between and within group? And you might have to ask how many populations are involved. I like to start out by asking what kind of variables I have. If I've got 2 qualitative variables, I know it's a chi-square. And all I have to do is decide if it's a 2 by 2 or a 2 by k. If I've got 2 quantitative variables, there's only 2 possibilities. Well, that's not quite true. If I've got 2 quantitative variables and I have a research hypothesis about an association, and I've got 1 population, I'm going to do 1 correlation. If I've got 2 quantitative variables, a research hypothesis about an association, 2 or more populations, I'm going to calculate a correlation in each population and compare them with Fisher's Z. If I've got 2 quantitative variables and a research question about mean differences, it's going to be a 2 between groups F. So this has been added in. This one just did. If I've got 2 quantitative variables and a research hypothesis about a mean difference, it's a 2 within groups ANOVA. So I can compare the means on those 2 groups. No, it's within, because I've got your pre-test and your post-test. Those are my 2 quantitative variables. And I want to know if there's a mean difference between them. I'll get there. If you've got 3 quantitative variables and you have a research hypothesis about which one is the best predictor, or any research hypothesis about how they're differentially related to each other, then you do all of those correlations and you compare them using Steiger's Z. If you have 3 quantitative variables and your research hypothesis is about a mean difference, then you've got a K within groups ANOVA. How are we doing? If you have 1 qualitative variable and 1 quantitative variable, you know it's an ANOVA. And the question you have to ask is, what kind of design do I have? If I have a between groups design with different people in different conditions, I'm going to do a between groups ANOVA. But I have to decide if I've got 2 between groups or K between groups. And if I've got 1 qualitative and 1 quantitative, I know it's an ANOVA. If my research design is a within groups design, it's going to be a within groups ANOVA. And I have to decide if I've got 2 groups or K groups. The sticking point in this whole process is that there's 2 different ways to get to within groups ANOVAs. Thinking about it as quantitative variables with mean difference hypotheses, or thinking about it as 1 qualitative and 1 quantitative variable. One's the IV, the other's the DV, and a within groups design. Now, what are we missing?
In terms of the second one, where you finally need to relationship ANOVA.
Uh-huh.
You started with two quantitative variables.
Yep.
Why can't it lead to different groups?
Because if I've got two, I see. Only under the circumstance where you've got a quantitative independent variable. But when you're doing an ANOVA, whether those things line up on a quantity or are categorically different, they're still different groups on a variable. And so what I've got is I've got two quantitative variables from you. Your score in one condition and your score in another condition. I can ask if they're related, or I can ask if there's a mean difference. Okay? Cool. Describe the different uses of Steiger's z-test and Fisher's z-test for comparing correlations. What questions need to be separated from the questions answered by these tests? All right. Steiger's z is for comparing correlations that come from the same population but involve shared variables, what are known as correlated correlations. The two correlations share one variable. There's four kinds of those. One distinction is whether you're asking which of two predictors is more correlated to the same criterion, or if you're asking which of two criteria is more correlated to one predictor. The statistic doesn't care if you're asking those two questions. It doesn't care if you're saying which is the better predictor for this criterion, or what does this predictor better predict, this criterion or the other one. They're just correlated correlations. The other variation is whether you're testing correlation differences that include the sign, or just strength of relationship questions that don't include the sign. So Steiger's z, one population, a set of correlated correlations. They might be one predictor and two criteria, or one predictor and two criteria. No. One criteria. Oh, shit. And it's recorded. Those could be two predictors and one criteria, or one predictor and two criteria. And we might be asking questions about correlation differences that include sign, or relationship strength differences that don't include sign. Fisher's t-test is used for comparing correlations between the same two variables that come from two different populations. And the good news is there's only two kinds of those. When you're comparing correlations that include the sign, and when you're comparing strength of relationship that don't. Now, what questions need to be separated from the questions answered by these tests? Both of these compare two correlations. They ask if the correlations are different from each other. Separate from that is whether or not each of the correlations is different from zero. So if I'm in a Steigered situation where I've got the correlation between practice and performance and prior experience and performance, and I want to compare those two correlations, the Steiger's test only tells me if those two correlations are different. I also need to ask if each of them is different from zero, because they are three different questions. Is correlation 1 different from 0? Is correlation 2 different from 0? Is correlation 1 different than correlation 2? Same thing in the Fishers. I've got two correlations from two different populations. The Fisher's test asks, is the correlation from one population different from the correlation from the other population? The other two questions are, is the correlation from the first population different from zero? Is the correlation from the second population different from zero?
Yeah, thanks so much. Almost 1 hour. I hope this helps some of the statistics students working on this kind of designs. It's really nice. I never did I never come across this kind of research, but it looks like this is really important for people involved in conducting experimental studies, and well, for us as a consumers of research, we always need to know what are the ways to say research is good quality or not good quality, if the evidences are strong or not strong. Yeah, and there is a quote which I hear from Professor Carl. He said, the best way to avoid someone cheating you is to know more than them. You see, if you don't know, always there is a possibility that you can be misled by people who know better than you or who would take advantage of your innocence. So anyways, thanks so much, Professor Carl. And yeah, as I said, I wish you lots of happy days. Please keep teaching. I know Professor Carl is going to retire. He's going to retire after a year, I think. So he's really, really experienced. And he made the very difficult course enjoyable and fun. I remember whenever I attend these very difficult courses, sometimes I just fall asleep or I feel disinterested. But nowadays, coming after doing some research and attending different conferences, I just see how much false positive, false negative, a lot of misleading information is reported, especially for those of you from nutrition department. That's the area I know a little bit better than the others. I remember a lot of studies conducting, let's say, predictors for height of children, why some children are tall and others are not, and what predicts nutritional status of children. I remember sometimes people just make, solve these false positive issues coming up. A lot of differences to say, children are taller because we give them education for the mothers, or because mothers are getting this kind of support and their children are growing faster and all these things. One of the topics we usually exclude is about variables, about fathers, or there are a lot of issues that we can discuss about if we practically discuss the application of what Professor Carl was telling us, especially in the design in early parts, like, for example, hypothesis and then all these sampling issues. I remember whenever people report sampling, people report about, including myself, we used to report how much people we included in a study. Then we say it's our sample size. If we have 1,000 population, then we take about 10%, okay, or we use single population proportion, double population proportion, or experimental design on all these things. But now I learned from Professor Carl, it's not only the number of people, but the first thing is the question you use by itself is one sampling. So you discuss about the population, you discuss about setting, you discuss about the stimulus and the kind of tasks. You also discuss about temporal time differences. Also, you need to discuss about social differences. A lot of studies, usually including the Ethiopian Demographic and Health Survey, are conducted during one season, and usually they don't discuss seasonal differences. We know in Ethiopia food availability highly depends on which season you are collecting your data. I don't remember when Ethiopian Demographic and Health Survey was reported across different seasons. You see, we do it once in 4 years, and it's reported only for one harvest time or one time of a year. And only make a lot of decisions based on this. So I hope gradually we grow out of this and then start making some very high quality. I know it's all depends on awareness of the researchers, the resources available, and the support from the environment. Anyways, yeah, I'm enjoying this thing, and it's one of the very nice classes I'm attending. So I wish you a very nice time. Please keep sharing. Sharing is caring, as we say. We don't know. At least one or two people might get inspired or be informed by this information. Thanks so much.